absolute convergence. What do I even mean by absolute convergence? Well, here's the definition, right? So definition, the series, I'll write down a series, the sum n goes from 1 to infinity of a sub n converges absolutely. So this is the term that I'm defining absolute convergence. I'm going to say the series converges absolutely if what happens? If the series, just the sum, n goes from 1 to infinity of the absolute values of the a sub n's, just plain old converges in the usual sense. What's an example of this? A while ago, so that this series, the sum n goes from 1 to infinity of the absolute value of sine n over 2 to the n, that series converges. You could prove that by doing a comparison test with the geometric series 1 over 2 to the n. All right, so that series converges, and that means that this series, the sum n goes from 1 to infinity of just sine n over 2 to the n, no more absolute value now, just sine n over 2 to the n, that series converges absolutely, or we might say is absolutely convergent, just because this series, the sum of the absolute value of this quantity, converges. But with a name like absolute convergence, you'd hope that an absolutely convergent series is also just convergent in the regular sense of converging. So that's a theorem. If the sum of the absolute values of the a sub n's converges, then just the sum of the a sub n's converges. In other words, if a series converges absolutely, then it just plain old converges. Let's prove that. Okay, yeah, so how's this proof going to go? Well, the proof is going to start out with my assuming that the series converges absolutely, meaning I'm going to assume that the sum of the absolute values of the a sub n's converges. And then somehow, I want to do something, I don't know what yet, so I've got some cloud with question marks, and then I eventually want to conclude that the original series converges. So what goes in these question marks, right? How do I get from this assumption to this conclusion? Well, the first thing I can note is that if this series converges, then the sum of twice those terms also converges. Why is that important? Well, here is the key fact. This is sort of a trick, if you like. But what it's saying is that 0 is less than or equal to a sub n plus the absolute value of a sub n is less than or equal to twice the absolute value of a sub n. Why is this even true? Well, let's think about the possibilities. Maybe a sub n is negative. And if a sub n is negative, then I've got a negative number plus, well, the absolute value of that negative number. These two things cancel, and I just get 0. And then certainly this is true. 0 is less than or equal to 0 is less than or equal to twice some positive number. What if a sub n were positive? Well, then I'd have 0 is less than or equal to a positive number plus itself, because the absolute value of a positive number is just that same number, is less than or equal to twice that same number. Well, in that case, these are equal, right? I've got a positive number plus itself. That's the same as twice that positive number. So if a sub n's positive, this is true. If a sub n's negative, this is true. If a sub n's 0, this is just 0 less than or equal to 0 plus 0 less than or equal to 2 times 0. So whether a sub n is positive, whether it's 0, whether it's negative, no matter what happens, this is a true statement. Now we can apply the comparison test. So now by the comparison test, this series converges, right? The sum of these converges. The sum n goes from 1 to infinity of a sub n plus the absolute value of a sub n. Well, that's term-wise less than this convergent series, and all the terms are non-negative. So that means this series converges. But now our original series can be written in terms of this series and the sum of the absolute values of the a sub n's. So what I've got is this series converges, but the difference of these two series is the series that I'm originally interested in, right? And the difference of convergent series converges. So that means that the series, just the sum of the a sub n's, converges, which is exactly what I wanted to show. So we proved the theorem, right? If a series converges absolutely, then it just plain old converges. And that really justifies the terminology. I'm calling this, well, everybody calls this absolute convergence because it's a strong kind of convergence. Absolute convergence implies convergence. So absolute convergence is even stronger than just regular old convergence.